Okay, so this is a continuation of the practice test, starting with number 13. I can write an equation from word to symbol formula. That's what it tells me some of these are going to be like. Then it says, look at the reaction below, which is the sum of the whole number coefficients when the reaction is balanced. So C3H8 plus O2, arrow CO2, plus HOH. Balance it alphabetically, so the first ones you want to do is carbons, then hydrogens, that gets me 8. Now do oxygens, and there's 3 times 2, or 6, plus 4 is 10, so I need a 5 right here. Remember, there's a whole number coefficient right here. It's not written, it's number 1. So 1 plus 5 is 6, plus 3 is 9, plus 4 is 13. So 13 is B. Number 14, which is closest to the number of grams in 0.5 moles of sodium carbonate. So we're going from moles to grams. So moles right here to grams right here. Molar mass on the top, moles on the bottom. And if I add up sodium carbonate, sodium's 23 on the periodic table, times 2, because there's 2 of them, plus carbon is 12, right here, plus oxygen, which is 16 times 3. So let's add those up on my calculator here and make sure that I got it right. 16 times 3 equals, plus 12 equals, plus 23 equals 106. So there's 106 grams in 1 mole, and 0.5 times 106 is about 53. Letter B. Next, it says I can perform mass, mole, and molecule stoichiometry problems. And this would be number 15, which is closest to the number of grams of bromine produced when 2 moles of sodium bromide is decomposed according to the following balanced reaction. So 2 moles of sodium bromide are decomposed. We put sodium bromide in a position where it's going to cancel. And which is the number of grams of bromine produced. So bromine are my new set of units right here. Following these steps, I'm already in moles. So now I need to do a mole-to-mole ratio right here. And the mole-to-mole ratio is a 2 in front of NaBr. And there's a 1 in front of bromine. And that would give me my moles of bromine. But now I need to convert to the asked for units down here. So lastly, I need to go from moles of bromine to grams of bromine. And if you forgot how to do moles to grams, remember we're right here and we're going to grams. So molar mass goes on the top. Bromine is 80 times 2 is 160. So 2 times 1 divided by 2 is 1 times 160 is 160 grams, which is letter D. Number 16. Which is closest to the number of moles of KBr produced when 39 grams of potassium combined with 80 grams of bromine according to the following balanced reaction. So now we're given 2 substances and we're given the balanced equation. So we need to convert both of them to moles. So 39 grams of potassium, 80 grams of bromine. Okay, careful, it's Br2. And after we convert it to moles, then we'll have to divide by the coefficient to determine the limiter, use the mole ratio, and then convert to any asked for units. They are asking for moles here at the end, so we won't have to do step 4. So convert from grams to moles. Potassium is 39 on the periodic table. If you look on here, here's potassium, 39. Bromine is 160 on the periodic table because bromine is 80 times 2 is 160. 39 times 1 divided by 39 is 1 mole of potassium. 80 divided by 160 is 0.5 moles of bromine. And now we need to do step 2.5, divide by the coefficient. There's a 2 in front of the K. There's a 1 in front of the Br2. And it turns out this would be 1/2, and this is also 1/2. Both of these limit. And so when you go to work the rest of the problem to find the mole ratio and find out how much KBr is produced, they're both going to be completely used up. You can use whichever one you want. Either one will work. So I'm going to use my 1 mole of potassium and for every mole ratio of potassium, there are 2 kBRs that are produced. So 1 times 2 divided by 2 is 1. So 1 mole of KBr will be produced. Letter C. Number 17, which is closest to the grams of oxygen in 100 grams of calcium carbonate? So there's a couple of different ways you could do this. I think maybe the easiest way to do this is to find out the percentage of oxygen in here. So if you find the percentage, remember that's part divided by whole times 100%. And the part that is oxygen is 16 times 3 divided by the whole thing. Calcium is 40, carbon is 12, oxygen is 3 times 16 or 48. So this is 60 plus 40 is 100 divided by 48, or 48 divided by 100 means we're 48%. So 0.48 times my 100 gram sample would tell me that there are 48 grams of oxygen inside of this. Letter D. Now there's other ways to do this as well. You could convert to moles, and then you could do a 3-to-1 ratio for the molecule as well. Either way you like doing it is correct. Number 18, which is closest to the number of grams of ammonia produced when 56 grams of nitrogen react with 24 grams of hydrogen? Okay, so this is a complete stoichiometry problem here. I'm going to skip to another page so I have plenty of room. Step number 1, write the balanced chemical equation, done for us. Step number 2, convert to moles, so 56 grams of nitrogen and 24 grams of hydrogen. Nitrogen, N2, nitrogen is 14 on the periodic table, so that's 28 grams in 1 mole of nitrogen. Hydrogen is 1, and there's 2 of them in the formula, so that would be 2 grams in 1 mole. So 56 divided by 28, let's just make sure we get that right. I believe that's 2, and that's correct. So there are 2 moles of nitrogen. 24 divided by 2, there are 12 moles of hydrogen. And now we're done with step 2. Step 2.5 says divide by the coefficient to determine the limiter. Nitrogen has a 1 in front of it. Hydrogen has a 3 in front of it, so this would be 2. 12 divided by 3 is 4, obviously. So we have 4 here. Which one's going to end up being smaller? Well, nitrogen is. So this limits my reaction. Now use this number 2 right here to work the rest of the problem. So now I need to do a mole ratio to determine the amount of ammonia that's produced. Ammonia is my NH3 right here. So nitrogen in a position where it's going to cancel. NH3 is my new set of units. For every 2 ammonias, there's 1 nitrogen. I get that from the balanced chemical equation right here. 2 times 2 is 4, so I'll get 4 moles of ammonia. And then I need to do the last step and convert to the asked for units. Well, the asked for units are grams of ammonia. 17 grams in 1 mole of ammonia. When you add up nitrogen, 14, plus hydrogen, 1 each, it adds up to 17. So 4 times 17 gives me 68. So there are 68 grams of the NH3 or ammonia that are produced. That's a full, good limiting reactant stoichiometry problem. Number 19, which is closest to the percentage of oxygen and sulfur dioxide gas? So remember that's part divided by whole times 100%. So the part that is oxygen is 16 times 2, which is 32. And then the whole thing is sulfur is 32 plus oxygen 16 plus 16. So that's 64. So that would be 0.5, or times 100% would give me 50% is oxygen. So that would be letter C. And then lastly, which is the possible molecular formula for an empirical formula that is C2H3O? So a possible molecular formula would be one where each one of these subscripts right here is multiplied by something, and it ends up being a whole number ratio. So for example, if it was multiplied by 2, C4H6O2, see how these are each multiplied by 2, could be a possible molecular formula. Let's see if that one's here. C4H6O4, nope, C4H6O2. Yep, letter D is right here. You could try multiplying by 3 and see if that's there, or by 4, or by 5, and see if that's there, but it turned out that this one was easy enough to find. Good luck.